Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video on the invertible matrix theorem. So the invertible matrix theorem has to be my absolute favorite theorem in all of maths because it just brings together all of these aspects of matrices that seemingly have nothing to do with each other and shows that they are equivalent. So what actually is the theorem? Well, what it is just a list of statements that are equivalent to a matrix being invertible. So what we mean by equivalent is that if one of these statements is true, it implies all of the others are true. And if one of these statements is false, it implies that each of the others is false. So these 9 statements that are on your screen, they are either all true about a matrix A or they are all false about a matrix A. So if you want to know whether a matrix is invertible, you have so many ways to check. So if a matrix is invertible, it means it has a non-zero determinant, 0 is not an eigenvalue, and so on and so on. That's what the theorem is actually stating. So note, I have actually left a few statements off here. So for example, there's one about singular values that we're not covering in this course. There are also some that we are going to get to later. For example, about the dimension of the column space of A. But for now, these 9 statements are equivalent to the matrix A being invertible. So it can be proved that these statements are equivalent. I'm not going to go and prove that each statement here is equivalent to the other 8. That would take too long. I'm just going to focus on the first 3 statements here and show why they are equivalent. Let's say I wanted to prove this aspect of the invertible matrix theorem, that a square matrix A is invertible if and only if 0 is not one of its eigenvalues. So there's 2 directions to this proof. So the forward direction, we're saying if A is invertible, then 0 is not an eigenvalue of A. And then the opposite direction, if 0 is not an eigenvalue of A, that means that A is invertible. So how easy this proof will be is determined by what we're allowed to assume. Are we allowed to assume the other 7 statements that were on the previous slide? If so, this would be really easy. So this first direction was that if A is invertible, then 0 is not an eigenvalue of A. So if we can assume the statements on the previous slide, if A is invertible, that means that Ax equals 0, here x and 0 are vectors, has only the trivial solution, that x is the 0 vector. So that would mean that Ax equals 0x, this time 0 is a scalar, implies the only possible solution is the 0 vector. But the 0 vector cannot be an eigenvector by definitions. So that means that there are no non-zero vectors x that satisfy this equation. So that would mean 0 is not an eigenvalue. That's a very easy proof. Now let's look at the other direction. Actually just reverse the logic here. So if 0 is not an eigenvalue, then Ax equals 0, this time 0 is the scalar again, has no non-zero solutions. We know, however, that x equals 0 is going to be the only solution to this. X equals 0 is always a solution to Ax equals 0x. But if 0 is not an eigenvalue, there will be no non-zero solutions to this equation. And as we saw in the previous slide, that implies that the matrix is invertible. So that was really, really simple if we were allowed to use some of those other statements. But what if we're not allowed to do this? Now we're going to look at proving the statement above without being able to assume that any of the other statements in the invertible matrix theorem is true. So we'll start with this direction. We'll assume that A is invertible, and we will show that 0 cannot be an eigenvalue. So the definition of being invertible is that if A is invertible, there is a matrix B such that AB is equal to I. So we can take the determinants of both of these matrices. So the determinant of AB will be equal to the determinant of the matrix I. But the multiplicative property of determinant says determinant of AB gives us determinant A times determinant B. That's equal to the determinant of I, which is always 1, regardless of the dimension of I. So what we have here, a scalar number times a scalar number is equal to 1. So neither of those numbers can be equal to 0. You can't multiply 0 by a number to get 1. So that proves that the determinant of A is not equal to 0. So we've actually proved another statement in the invertible matrix theorem, that if A is invertible, its determinant is not equal to 0. What does this have to do with eigenvalues? Well, remember that lambda is an eigenvalue if and only if the determinant of A minus lambda I is equal to 0. So if 0 is an eigenvalue of A, then what we have is that determinant of A minus 0i would be equal to 0. But 0i is just the 0 matrix. And that means that the determinant of A is equal to 0. But that's a contradiction, because we just figured out if A is invertible, the determinant cannot be equal to 0. So we've proved here that if A is invertible, it has a non-zero determinant. But if 0 is an eigenvalue of A must have a 0 determinant. So those things are contradictory. So if A is invertible, it cannot have 0 as an eigenvalue, because that would mean its determinant is 0, which we proved can't happen. Again, going the other way is just sort of using the logic but in reverse order. So if 0 is not an eigenvalue of A, then that means that the determinant of A minus 0i cannot be 0, because 0 is not an eigenvalue. So that means that the determinant of A is non-zero. And if the determinant of A is not equal to 0, then we will be able to find a matrix B with non-zero determinant that it will be able to be multiplied by to get I. If the determinant of A is not equal to 0, then all of the methods we learned of how to find the inverse in the previous lesson, they will work. You can also make other arguments here as well. If the determinant of A is not equal to 0, then the columns of A are linearly independent. There are heaps of arguments you can make here. But if we're just sticking to not using the statements on the previous slide, if 0 is not an eigenvalue of A, then the determinant of A is not equal to 0, and therefore there will be a matrix that you can multiply it by to get the identity matrix. Alright, that's just one aspect of the proof. You will look at proving some of the other statements in the lessons. This is a wonderful theory and it's very important. Hope you enjoyed as much as I do. This has been the luckiest maths teacher in the world. Have a great day.